Okay. So yeah. So let's continue. So the question was, why did we not why did we solve the Bayes rule in that case? Yeah, regarding the way the probabilities are computed are in some ways we are saying that based on Bayes theorem, okay, then the ABS is a way of a shy uh, way of expressing the Bayes theorem. And so what we are looking at is there a shortcut? Why is this shortcut possible? So we are trying to explain why that shortcut is possible. Let me record. We are starting. Yes. Why that shortcut is possible. There must be an explanation. Okay. So now what we are saying. So let's write, because my board is already I didn't it was erased after the time ran out. Okay. So let me record. We are saying that maybe here is better. We are saying that what is the probability of Bob defaulting CJ given his attributes D. Okay. And so in that example, in this example here, it says that it is computed by the known attributes given the expected classification multiplied by the classification. Okay. But we are saying, okay, so this is the case. And so we say that this part was this part, all the attributes. Okay, because we by chain rule dependency, we are saying that we can write this in each attribute, Cj multiplied by the second attribute, D2 given Cj, multiplied by the third attribute given Cj. Okay, so this part is the same as this part, again multiplied by the Cj. Okay, so but we know that in Bayes theorem, if we are asked to compute for the classification given the attribute, you will have the same expression on the numerator, but you will have a denominator that is the probability of the attribute. What happened to that one? Did we assume that it is a 1? And if we assume it is a 1, is that possible? Then, well, let's compute. The way to verify it is to compute. Okay? So we say that probability of D of the attribute is equal to, we just follow whatever is written here in the equation here. Probability of D. So where is the original Bayes rule? This one. Okay. This probability of D. And so we can write it as, in this case, we are not given that. So we compute this based on the Y, which is the Y that's given based on CJ. So probability of D given CJ and probability of CJ multiplied by the other CK. So now let's do that. So it's for us to continue. So probability of D given Cj, okay, plus probability of a D, sorry, multiplied by probability of Cj, which is in this case we want to not default, plus probability of D given Ck. For example, Ck is the one that is defaulting times probability of Ck. Okay, so let's go down. If we compute this on the table, can we give an answer whether this is one, just for an exercise, because we want to verify that in fact what this example is doing is correct. Okay, it is correct if indeed it is verified by based on the Bayes theorem that this particular equation is has is equivalent to the original Bayes theorem, or is there, if there is an assumption, then we should say that yes, this assumption is correct, because based whether we compute it by ourselves, this will return one. And so by doing that, we're saying that this information that we want, whether the Bob will default the loan given his attributes, can be computed by the attributes given the loan, and attributes given the default, he will not default, and then multiplied by all the attributes individually, then multiplied by the possibility of the attribute of the defaulting or not, absolute probability. Okay, so can we do that? Okay, so now this one, what is this? This part is the same as that, so that part is this, so that part is that. Okay, then we compute, what is this? This is the probability that he will default, this probability that he will not default, and this is probability that he will default. Okay, then we can see probability of Bob will default is 0.65, probability that he will not default is 0.11. This is not equal to 1. Is that correct or no? It will be correct, it will be similar. I mean, what I'm trying to discuss here is that to prove that this equation is correct. Why? If you write it formally, if you write this formally, this is equal to just the numerator of the Bayes rule, only this part of the Bayes rule. Okay, but if you are saying that the denominator is 1, then we can compute. But what is this? So we are trying to compute, I'm trying to compute now that in fact it is 1, but no, it is not 1, because this part here is actually the numerator. Okay, do you agree with me that this part are two parts, only in the yes and the no part? So I can write it down as C1. Okay, C1 being the no, just so it will be clear. This is the no part, or it will not default, the no part. And then this is the yes, it will default. Bob will default. Anyway, so if I draw it, C1, that is the no, he will not default. And C2, that is the yes, he will default. Okay, so if I expand this, so that means that the same thing, you will have D1, and given that yeah, given no, he will not default, and then probability of a D2 that no, he will not default, and probability of the D3 that no, he will not default, times probability that no, he will not default. Okay, then you add, then now is the same thing, probability of the D1 given that yes, he will default, probability of a D2 that yes, he will default, probability of a D3 that yes, he will default. I mean, yes, he will default times probability of is correct. Well, well, we have everything. If we look at this one, we have everything that we need. We can compute. So in this case here, probability of a homeowner, marital status, no married, these are all Bob's information. The same thing, D1 homeowner, no, marital status, married, and child experience 3. So D1, D2, D3. So these are all D1, D2, D3, given that no, he will not default. Given that no, he will not default, multiplied by the no, he will default. Multiplied by the no, that he will not default. And then here is the same case, D1, D2, D3, but now it is a yes. And so this equation here, I mean this value here is, and this value are added. So that means that this value is that and that value is this, but it does not equal to 1. And so what are we saying? If they're not equal to 1, that means that this Bayes rule, okay, let's just write it down. This part is that 0.065 plus 0.11. So how much is that? 0.076. It is not equal to 1, and so it is not equivalent to the Bayes rule. The computation that is given to us is not equivalent to the Bayes rule. What does it mean? Is this the correct computation that is given? What does it mean? The question is, can we get uh, a good judgment of whether Bob will really default or Bob will not default based on our computation? Remember, what we are doing here is just an estimate of the Bayes theorem. is not exact Bayes theorem. It's a shy Bayes theorem. It's an idiot Bayes theorem, but is the result, even though it's a shy, not the exact probability, will it give you some sort of a probability that will help you decide?
So I think it will.
Yes.
Yes, Mr. Inwaku, you have something?
Yes, I think it will give
Increase
us
your volume.
meant to decide. So we can compare the probabilities, the two probabilities, and come up with a
We are
judgment.
not hearing you, Mr. Okay, hold on. How come I'm not hearing you? Wait. Okay, now, can you say something?
Okay, so
Okay, now continue. Yes.
I think it could still give us a better judgment looking at the two probabilities that he will either default or not default.
Why?
Uh, there's a significant difference looking at the two probabilities, even
There
though
is a
it's not.
significant, sorry? There is a significant difference.
Yeah,
Okay.
0.065 and 0.011.
Yes. And so
So we could conclude that Bob will not default.
we can conclude. But,
Yeah, or make a judgment.
okay. Yes, we can conclude, but that Bob will not default. Yeah, that judgment is correct. We can conclude that. But based on the Bayes theorem, how is this conclusion related to the Bayes theorem, which we have seen that it is not equivalent to Bayes theorem because the probability of the denominator is not equal to 1. It is not equivalent. But the judgment will be still the same even if we compute the Bayes theorem. Our judgment will still, of Bob not defaulting, will still be the same. Why? But yes, your answer is correct. But the question is why? Why will it be the same judgment? If, for example, if you compute the Bayes theorem here, if you compute the Bayes theorem, what will happen?
Yeah.
The result is divided by 0.076. You're almost there.
Oh,
If you compute the Bayes theorem, you what we are saying here is that this computation here, if you remember, these computations are just the numerator of the Bayes theorem. That's what we are saying here. Remember?
So,
Okay. This one is
so
just the numerator. There is a denominator that is the sum of these two, which is 0.76. That means that for Bayes theorem, this one will be divided by 0.76. And this one will also be divided by 0.076.
yes, sir.
Will it matter? It
No, it
won't.
will not matter since you are dividing by the same
Dividing
variable.
exactly the same number. And so Bob will therefore not default. Maybe the probability is the exact probability as the Bayes theorem, but the judgment is still the same.
Yes, sir.
Are you, Mr. Boho, do you agree? You look... Okay, let me do it one more time. This is very important.
Oh,
I'm
what you
sorry,
wanted to say to me?
it didn't come very clear in these slides, but let me clear everything and repeat it. Okay? I want to repeat it because it's very important. Okay. So what we want to do here is actually we want to know whether Bob will default. Okay. Will yes or no? What is the answer? Default? No, will not default given his attributes. given the D attributes. Okay? Okay. So now, what is this? Okay. Well, we are given already an equation here, but we don't want to take it as it is. We want to understand it based on our understanding of the Bayes theorem. Okay? So now we want to know whether this equation is correct. Okay? So our understanding of the Bayes theorem is that if you are given a y, an output, we want to know the output given the attribute D. Okay? So Bayes theorem is probability of, okay, we will just exchange that, of a D given a Y, probability of Y, yeah, divided by probability of D. That's Bayes' theorem. Okay? But in this example, what this example is doing is that it's not doing that. It's only doing probability of Y given D. It's just saying that that is equal to the numerator only. dy d probability of D, probability of Y times probability of Y. That is what it is saying. Okay, why? Well, we are saying that this can be written as by the dependence chain rule of probability. You can write it as D2 probability of Y. Oh, sorry. Undo. Okay. Probability of Y times probability of D3 probability of Y times probability of Y. Okay. That's the equation that this is doing. Okay, undo that. That's the equation that okay, these two, these three, this one, and that one, that is that part. Okay, see, probability of homeowner, that's the attribute, and probability marital status, that's another attribute. Probability of job experience, that's one another attribute. So all these three attributes are these. Okay, multiplied by probability of the Y, the absolute probability of the output, probability of the no. So this is the absolute probability. That's that one, which represents that. So actually, we are saying that this computation of Bob not defaulting is just the numerator only, the numerator of your Bayes theorem. And we are saying that it is enough. Why it is enough? Although that when we compute the P of D, it is some value, it is not equal to 1. It is equal to 0.076. Well, because we are looking at two probabilities. One probability is that probability of Bob being a no, he will not default given his attributes, and probability of the yes, of a yes, he will default given the attribute. Okay, so if we do that, then you are just doing the numerator and the denominator is the same. So I mean, if we compute the numerator, you're okay. Maybe okay. Wait. Maybe I should just y1, y2 so that it's clear. Okay, so probability of y1, which is the no, and the attribute is equal to probability of okay, d1. Okay. Do you understand? It's hard to it's hard to write here. Probability of a D a given y1, probability of y1 okay, over probability of the D. Okay. And the other equation is we are saying probability of a y2 meaning he will default, probability of y2 given the same attributes, yeah, given the same attributes is equal to probability of the attributes given y2, which is the yes, he will default, and probability of the y2, yes, he will default, divided by probability of the same attributes. Okay, we computed already that the attribute. Okay, and then we are saying here that we're only interested whether Bob will default. This is the case, will Bob default? We'll interested if Bob will not default or Bob will default. Okay, so our computation, the computation that's given is that we only compute the numerator. We compute the numerator, this numerator, and we also compute that numerator, and we already decide, yes, he will not default because the probability of him not defaulting is higher than the probability of him defaulting. And so we judge, yes, he will not default without even knowing the value of the denominator. Without knowing the value of the denominator. Well, we don't need the value of the denominator. We can already know the judgment because the value of the denominator for both of these cases will be the same. Okay? So whether we divide this by 0.076, it doesn't matter. We still get established the fact that Bob will not default. Okay, sorry. Whether we divide this, okay, is that understood? I'm just caught up with this explanation because you 0.076, and so these computations are correct. They are good enough even though we are not computing the entire Bayes theorem. Okay? Understood? ¿Entiendes? Yes? Okay.
Yes, sir.
Okay, good. Clear all. Let's move on. Okay, with the rest. 3 more minutes. This one, the last example. This one is nice example. That's why I hold this one. Okay, let's just go until 1 o'clock. Okay, so now, okay, we're done with that. We're okay with this one. So now this one. So I like doing diseases because that one is a little bit, interesting. And now is about pandemic, and then all of us are scared about all the possibility of having contacting the disease. But that now we'll calculate the probabilities of us having disease. Okay, so now we are given this information of the data of people with certain occupation, nurse, farmer, and builder and teacher, and then symptoms of the ailment, sneezing and headache, just 2 symptoms. And then we can already say what's the kind of ailment. If you're sneezing and you're a nurse, your sickness must be a flu. Something. It's a very simple interpretation, but yeah. We want to know, based on this data, if it's sneezing and that person's occupation is a builder, what kind of ailment that person has based on the data that is given to us. Okay, so how do we write it? Okay, we of course we say we do Bayes theorem. I mean naive Bayes, yeah. So we start with the Bayes theorem just to be safe. Okay, so now what is the Bayes theorem? We want to know what is the ailment. A being the ailment, okay, given the symptom and the occupation. Okay? And so, how do we write this? Probability of the symptom and the occupation given the ailment multiplied by probability of the ailment divided by probability of the symptom and the occupation. Okay? So how can we solve it? What kind of ailment? Oh, okay. What is the question here? Let's solve first. Clustering, probably, let's say, oh, there should be a question. What ailment should we predict for sneezing, a builder, and why? What ailment? Okay. So we have to know what is the probability that the okay, that means that there are three types of probabilities here: flu, hay fever, concoction, concussion. Yeah, flu, hay fever, and concussion. Yeah. So that means that we need to know the probability of each of those ailments. Okay. So for example, we need to know whether okay, because the denominator are all the same, we don't need to compute it. Okay. There are three possibilities. We want to know whether the sneezing builder has a flu, or the sneezing builder has a hay fever, or the sneezing builder has a concussion. Okay? So that means that we don't need to compute this. Okay? We only need to compute that because the denominator for all of them is the same for all those probabilities. Okay? So now we say that probability of the builder having a flu, an F, given sneezing and why did I put O here? It should be occupation, symptom, occupation. Given symptom as sneezing, sim undo. Symptom as sneezing, and occupation as the builder, B, small b. Okay, so let's just let's assume, okay, just to be easy, let's just do small one, small s, sneezing, and builder. Okay, so now we write this as probability of sneezing and builder given flu. Okay, and probability of flu. Okay, that's one. The other one is probability of hay fever given sneezing and builder is equal to probability of sneezing and builder given hay fever and probability of hay fever. Then the third probability of flu, concussion, and sneezing and builder. What is a concussion? Is that like the head? You get SB probability of a concussion, given concussion, probability of concussion. Okay. Okay, there. So let's compute. What is probability of the flu? This one is fast. So what is this? Flu. 1, 2, 3. 3 out. 1, 2 out of 3. 1, 2, 3, 4, 5, 6. So that's 3/6. Okay. Probability of hay fever. That's 1/6. And probability of the concussion. That's 1, 2. That's 2/6. Okay. And then now this one. Given flu, what is probability of sneezing? And that means that here we can say probability of sneezing given flu again, because we say the attributes are independent. Probability of the builder given flu. Okay, so let's look at flu. So flu. So probability of flu and sneezing. Flu, sneezing. There are three. So sneezing is 2 out of 3. So okay, let's just do here 2 out of 3. And then the builder, flu and builder. Builder is 1 out of 3. So 1 out of 3. And here that's 3/6. Okay, then the second equation, probability of hay fever. So hay fever given sneezing, hay fever and sneezing, that's one, that's one. Yeah, so that's one times probability of the farmer and hay fever, that's 1 over 1 times probability of hay fever, that's 1 over 6. Okay, and the third equation, probability of sneezing, probability of concussion and sneezing, 1, 2. Concussion and sneezing, that's 0. Zero probability. It's become zero, but anyway, there's a way to compute a zero probability. We should not use this one, but anyway, let's just write it. Probability concussion and a builder, that's 1/2. Okay, times 2 over 6. Okay, so which one does the higher probability? Okay, this one by default is not a correct computation, but anyway, there's a way to deal with zero probabilities, which we'll discuss later. But let's compute this one and the other one. How much? Which one is bigger? This one is 1, and that's 3, and this one becomes 1. And so this one is 1 over 9, and this one is 1 over 6. So which one is big? He must have a high favor. I mean, this is 1 over 6. Is that correct?
Yes, sir.
Turns out the builder has flu. Ours is wrong. Ours is hay fever. How come our... no, this is correct. 1 over 9. Our computation is 1 over 9. Here is 1 over 6. Flu and sneezing. So they were just... Oh, ours is wrong. Why ours is wrong? Okay. Let's go here. So how did we... Flu, sneezing, and builder flu. Flu. Yeah, the same thing. We are computing exactly the same way. Clear all. We're computing sneezing and builder flu given flu divided by this one. So we don't compute, he still compute this. He only compute the entire Bayes rule, Bayes Theorem point 66 for the probability of the builder. I mean probability of having a flu. And this is big already, so he stopped. He didn't compute the rest. You understand? But do we agree with this one? So probability of the flu is 1 over 5. This is 1 over 5. Oh yeah, that's 1/2. Yeah, we know that this is 1/2. And sneezing and flu. What did we have before? Can we undo? Okay, there. We have is this 1/3 times 1/3. I think we committed a mistake here. That's 1/6. I mean, that's 3 over 6. Why ours is 1 over 9?